Good morning. This is question number 10 on partial fraction equalization. I'm trying to decompose it on the board. Have you guys finished question 10 yet? Any problem with question 10? So I'm trying to decompose. Basically, I'm trying to rewrite the fraction so the integrate will be easier. So let's try to finish the equation of the function itself, and then we'll go back to the integration part. The first entire process of rewriting everything. As you can see that the x cubed and x to the fifth has common factor. So if you factor the denominator, you will have 3 factor of x and 1 factor of x squared minus 1. So the x squared minus 1, x squared plus 1. The x squared plus 1 will give you this like one of the summation in the decomposed format, give you 1 term. But then the x to the power 3, that's power 3. So then the factor x actually going to give you 3 different terms that's in your summation. The reasons for that, you see a bit backward, like all these added together to give you this. So if you have x to the degree 3 in the denominator, you have to have every one of these because you want to have the numerator to cancel each other out. All right. So it's really the plan that we were talking about in 6.4. So now, in order to finish the calculation, we have to make sure we get the right number of A, B, C, D, E, F, and then plus up at degree 3, and that one being degree 2, so the numerator has to be degree 1. We have 5 numbers to solve. So any plan, it's like, how do we solve this? So what do we do first?
You multiply everything by x cubed, multiply by x squared plus 1.
You multiply both sides of the equation. Okay. So if you multiply both sides of the equation by the denominator, then we will have a 1 in the denominator, 1 on the left. And here it's going to be x times. We're multiplying. This is what we multiply to both sides of the equation. So the x will be canceled with x cubed, x squared. So you have ax squared. One of the x is canceled with the denominator x. That's the first term. Second term, if you multiply by the green term, the x squared will cancel the x cubed, and then you have 1 x left. So you have bx. You have the x squared plus 1 multiplied. All right, the c. X cubed will cancel the x cubed. So for c, we will multiply x squared plus 1. The dx plus f, we multiply by the denominator x squared plus 1 is canceled, we still have the x cubed. So that's what we have after we multiply both sides of the equation by the denominator. Now it's time to solve 5. We need to solve. So there has to be some shortcut to make things easier since we have 5 unknown numbers to solve. What do we do first? One number we can try 0. We can try and make x equal to 0. Let me rearrange things so the equation thing they're breaking into 2 separate lines. Summations. Okay, it looks a little bit better. We have the plus, so they're all in the same line. So number 1, let's make x equal to 0. Right. Remember, this equation is supposed to be true no matter what's the x value. Left side should put to the right side of the equation. So if x equal to 0, a times 0, or everything in this multiplication is gone. There's x in here. If x equal to 0, this whole thing is gone. There's x in here, x cubed in here. So the df is a, b, c, d. I didn't write e, but anyway, d and f is gone. So that x equal to 0 would have a c. So if you make x equal to 0, your equation literally becomes 1. Right? Okay, so we solve only 1. So obviously, every time you try this thing, you solve 1 variable. Okay, so we do have a lot of numbers to solve. And what do we do next? X equal to let's try x equal to 1. It's going to be slightly harder to do. Because we don't have a lot of numbers to try. 0 maybe the only one. So x equal to 1, we will get 1 equal to. This is all equal to 1. This is all 1. The 1 plus 1 is 2. So that's 2a. That's 1. So that's 2b. Remember c equal to 1. So that's related to 1 plus 1. And then d plus f. Plus d plus f and x equal to 1. That should be it. So we wouldn't be able to we won't be able to solve anything, but at least we have another equation, right? Since c is solved, out of 5 numbers that we need to solve, now we have 4 numbers to solve. And remember, if you want to solve 4 numbers, you have to have 4 equations. And right now we only have 1 equation. To solve a, b, d, f, c is considered done, so we can solve a, b, d, f. That's 1 equation. To get 2 more equations, 3 more equations, we have to try and think about other numbers that we try, such as x equal to -1. Did I hear -1? Right? Let's try -1. So let's try it. So things are getting a little bit complicated. Let's in the same equation we make x equal to -1. So if x equal to -1, we have 1 equal to the third -1, -1 squared is still 1, so 1 plus 1 is still 2. That's -2a. X equal to -1, so that's -2b. That's x -1 squared is still 2, so it's positive 2c. -1, so this is -b plus f. So that's another equation. 1c, we don't have the c, right? C equal to 1. C in our equations. C equal to 1. Just 2. So minus b plus f. Okay, so one thing we can observe is between these two equations and one and negative is opposite. If we're adding these two equations up, the negative 2a plus positive 2a would be 0, the negative 2b plus positive 2b would be 0, and then the negative b plus positive p would be 0, right? Right? So if we combine these two equations together, we would be able to solve for f. The point is a, b, d will be gone. We only have f, so that reduces number of
Shouldn't the B be positive and be negative because the X cubed negative one?
Yes, that makes sense. That's negative, that's negative. So this is x to the fourth. That's positive, that's negative. Thank you. Good catch. I was definitely wrong there. So this is gonna be positive. This is. All right, thank you. So we would try to combine the two equations. Let's call that equation 1, even though we already have a couple equations. Let's call that equation 2. So the point is you are adding these two equations together. Then the left side is 1 plus 1, which is 2. The right side, A is gone, B is gone, and F is gone. The right side is equal to 4 plus 2B, 2 times B. All right, so then D with the 2D would equal negative 2, and D will be negative 1. So at least we now have C and D, and remove one more variable. And any questions so far? Right, having negative 1, positive 1 actually equation. So this is the idea. We can, because the truly try opposite number might only work one time if we can't do this over and over. But wait, do you see the process how we get number? So you okay there? So now we have C and D, but we have 5 numbers. We have to solve 3 numbers. Let's put the number in there. So after we solve the D, then equation 1 and 2 are now equivalent, right? Once you fill in the D is negative 1, and that's negative 1. That's negative. That will be a 3. This is negative 1. Negative 1, 2 minus 1 will be 1. And this will be a 1 here. So this equation will be equivalent. That's not equivalent. Right? They're not proportional, so they're not the same. They're still statistical equation. Right? Right? Then after we solve for the D, I was thinking about equation 1 and 2. Are they going to be combined together into one equation? This is 1 and negative 2. That's 1. There's still 2 equations. I'm counting number equation and trying to consider what we need to solve. We solve the D. So after we solve the D, then we have 5 numbers to solve. 2 is solved. We have 3 numbers to solve. Right? Fill in the D number for D. We still have 1, 2 equation, and having one more equation will be solved 3 variables. Right? So I'm trying to think about what was the maximum try. I have to do this thing over and over until all the numbers is solved. Yes.
Okay. I did this problem.
Yes.
Fine.
Yeah.
And like I looked up like how to do it online, and it's only a different way. It's only like where it's separated the numbers differently. And like it worked out that you didn't have to go through the number thing, like the special numbers. And you're just able to integrate one of the how it's separated. You want me to tell you how it's separated?
Yeah. So you mean when you match the position? For example, is that saying that we distribute this?
I ended up separating it into.
Oh, you see, did you have your calculation number? All right. Yes. Okay. So the partition is different. No, that's after you got the coefficient. So how do you get the A? Okay, so it's already given it to you.
That's what happened, okay.
Right, that's what happened. So they knowing the ABC already, but we are just in the
Yeah.
process of finding the
Yeah.
determinant value. Yeah, the computer, but it's actually give you the partial fraction equation without explaining it.
Yeah.
But we kind of have to know why is
Right, yeah.
A equal to one and A equal to negative
Yeah.
one and B equal to zero and so, yeah. So anyway, okay, so we don't have to do this forever, like we have 5 number, the maximum number equation, the maximum number we have to try this is 5 times. But occasionally, if you look at the coefficient, it works out nicely, then we don't have to do this 5 times. We're just trying to lower the number of things we have to do. So right now, we already did it 3 times, and out of the second try and third try, finally, we already get the D. So now we have 3 more numbers to solve, so we already, that one is not considered an equation anymore, right? So this is the equation which has unknown. So we still have 2 equations that has unknown. So we should work out 1 more numerical equation, and then 3 equations, we should be able to solve A, B, F. That was the plan, right? So right now, we already know a couple of these already. D with -1, so this is negative, SC is 1, and then we don't have the rest of them. And according to your equation, the 1 was okay, the B is 0, the A was -1, but we still have to solve it in order to know all that. And what we can do is actually, since we have enough space, write down the equation that we had so far, and then see what they lead us to. And the first equation will be this equation. I'll make this. We already have C and D, so let's solve A, B, and F. This, I'll make that over. And we have 1 more equation, which is that one. It's still available. Right, so that's the second equation. And we combine this equation to D, and after we've done that, we already know that the D was negative. We add these 2 equations together, we end up having D equal to -1. If everything is right, it's cancel the common factor. So we add it all together, F and B and A will be canceled, and that gives us opportunities to solve for D. But at least after you know the D value, and you can then remove it by the actual number in there, and that will look like this. So that's -1, and that's -1. 2 plus -1 actually equal 1. So equation looks like this, and so we have 1 is equal to -2A but minus 2B. And then 2 plus -1 is 1, so plus 1 minus F. Okay, that's 1. And then the second equation below, after you put in the D equal to -1, is 1 equal to 2A plus 2B. And then plus 1. The 2 plus -1 is 1, and then plus F. They are the same equation, so if you combine them, I was worried about having the number billion, that it's gonna really combine this 2 equation. And the 1 and the 1 will cancel, right? 1 and 1 will cancel, and you have the F can move to the other side of the equation. So you're gonna get the same results, that F is equal to -2A, -2B. So we are gonna get this conclusion. So these 2 equations essentially the same equation. To solve ABF, you'll need 2 more equations, right? If you have 3 unknown, you need 3 equations to do. So I was gonna try to lower the number of try, and then looks like we have to try it 2 times. A, B, F, there are 3 numbers that we don't know. And you can do it the other way around. I thought you might try the other method that is matching the coefficient. For example, maybe that was better. You can see from this side equation, there's dx and x cubed. and there's ax to the x squared times x squared, that's the degree 4. And there's no degree 4 on the left side. So a plus d has to be 0. We have d equal to -1. Does that make sense? Maybe that in this particular example, matching coefficient might be faster than to try all these. Okay, there's not like maybe I have to try go even further. Like this is 3 variable and I have to have 2 more 3 variable equations to solve. All right, let's try to match the coefficient instead. There are 2 methods we can match the coefficient of both sides of the equation, or we try special value. I tried special value Vx. It looks like it's a lengthy process. After finding B and A, maybe I should try. Always try to look for a shortcut to lower the scenario that we have to try. And if you want to try further, you can make x equal to 2, x equal to -2, to try more in order to solve A, B, and F. And out of this equation, we can actually do better. For example, they match the coefficients. If this is the degree, this is what's on the left side. This is what's on the right side. For example, the left side for the degree 0 term, the left side have 1, okay? And the right side have, those are degree 2 and degree 4, degree 1 and degree 3. That's degree 2 and degree 1. There's a C. And there's a degree 3 and degree 4, so C. So if you match the degree 0 term, the left side have a 1, the right side, the only degree 0 term is C. So that indicating C has to be 1. Okay. And then there's degree 1 term. All right, left side does not have any degree 1 term, right? There's no degree 1. Okay there? And then the left side has no degree 1, so the coefficient actually 0. The right side of the equation, and that's degree 2 and degree 4, degree 3 and degree 1. So there's a B. The right side has B. That is degree 1. That's degree 1. And degree 2, degree 1. No, degree 2, degree 0. And this is degree 3. No, that's degree 4 and degree 3. That's it. So this is indicating C got equal to 1 and B has to be 0 because B is the only degree 1 term on the right side, but there's no degree 1 term on the left side. So B has to be 0. That kind of explains why, right? Okay, did I lost you? Yes?
What about the axis and that's what we can work on?
Yes, that works. That still means that if you are solving, it's possible. I just feel like it's more time consuming. You can leave it on one side and you have 2a plus 2b plus f equal to 0. We will have a, like you said, augmented matrix to have a 3 by 3 matrix that use the inverse matrix. You can solve the A, B, and F. But that's assuming that you have more equations. See, these equations are combined. Right now, we only have one equation. So we have to make x equal to 2, x equal to -2 to create 2 more equations. Then we have a 3 by 3 matrix. So that still with that approach, I still feel like. And so for this particular example, it's a lot easier. Just look at left side and right side, the coefficient for every degree terms. Okay. Yeah. So we're up to degree 1 term, and then we already find C and B. And then there's degree 2 term. We can solve it. There's no degree 2 term on the left. That's a degree 1 term, degree 0 term. So we have a 0 on the left side, on the right side, degree 2 term. This is degree 2. So maybe a couple. Then we have A, and then that's degree 3 and degree 1. This is degree 2 term. So we have a C. That's degree 2. And this is degree 4 and degree 3. That would be it. So we would have A plus C. That's the degree 2 term, but then it's 0. So we will have A plus C equal to 0. Since c equal to 1, that means a equal to negative. So we can identify. Do you have questions? Does this work? Is it okay? We're just looking at the different terms. There is several degree 4 terms, and there's also degree 3 terms. But through the degree 0, degree 1, degree 2, we already have the A, B, C. I think the table is a little too short. And then let's see, we also have degree 3 term. There's no degree 3 term on the left side of the equation, but degree 3 term, right? That's degree 2, degree 4. This is degree 3 and degrees 1 times 2 is degree 3, degree 1. Degree 3 term is B. That's degree 2 and degree 0. This is degree 4 and degree 3. There's an F, B plus F. Okay, so on the right side, the coefficient for the degree 3 term is B plus F. On the left side, equal to 0. Since they equal to each other, B plus F equal to 0. And we already know that B equal to 0, so we get the idea that F has to be 0. So then 0 plus 0 equal to 0. So that explains that F is actually 0. Any question? All right, so we have A, B, C, and then F. Lastly is B. That's the degree 4 term. On the right side, there's no x to the 4th power, so we have 0. On the right side, we have A for the degree 4 term. And we also have this one, the dx, so there's a d that has degree 4. And A plus D equals 0, and A was negative 1, so D must be positive 1. That doesn't make sense. We already have B equal to negative, which A is negative. It goes against understanding to what I get that number. Let me look at your, you said you already have the answer. Right. So dx plus f, that means d equal to 1 and f equal to 0. So this is d equal to 1 then. Okay. So these are right. What happened to the other calculation? And adding these two. So this calculation was wrong. X equal to negative 1. Right, D is negative 1, so this must be negative, but that's. Okay. So the calculation was wrong. I'm just trying to look at what was called a mistake. The D should be positive 1. This table here, I have to, with a special value method, I do run into a lot of trouble, and it's a lot more time consuming. So I feel like for this particular question, it's easier to match the coefficient. So you look at the degree of the polynomial on the left side and degree of the polynomial on the right side, and simply try to match up their coefficient. Their coefficient on the left side should equal the coefficient on the right side. So kind of match them 1 by 1, and then we might have a way to calculate the coefficient faster. Any questions? I don't know. Hope I explained. Have you guys done this question already? No? Okay. So based on what we already have, we have the ABC is -1. This is -1 and B was 0. And that was supposed to be +1. B is +1, F is 0. So then the whole thing is now expanded into this equation. So basically, we get to rewrite the calculation of 1 over x to the 5th power plus x cubed dx. Turns out the x is coefficient -1. The b is coefficient 0. The b is coefficient 0, so we don't have to have that term. C is equal to 1. So then it's 1 over x cubed. Plus the last one is x. C, b with 1, that we calculate over here. To 0, so we don't have that zero one term. This is x squared plus. Right, so what we were going through is this is a partial fraction. We rewrite that in that fraction into several small fractions, and I'm gonna integrate them one by one. The first one is a degree 1 in the denominator. Remember how to integrate that one? How we integrate 1 over x? Yes, so it's natural log of x. It's negative log of x. Now that one, you can consider that being a negative coefficient, that negative power, x to the -3. So that integrated into use power rule, right? -3 plus 1 is -2. So that's going to be x to the -2 power over -2 increased power. And we can move combine coefficient. And then the last one, you can see the denominator is degree 2, numerator is degree 1. So you can use the natural log, use substitution. U equal to x squared plus 1. So the denominator is u, numerator is 1/2 u. So that gives you 1/2 natural log of u, and u equal to x squared plus 1. So that's will be the answer. And that's pretty much how we integrate everyone. So the decomposition part is really the main part. We have to find a way to understand the process. Any question? For the one that doesn't have a lot of coefficient, I think look at the degree 2 term, degree 1 term, degree 4 term. Look at the coefficient on left side and right side and set them equal, maybe faster than have to try individual x value. It's the level of difficulty gets more and more if we don't have special value. We have to try general value of the x value, and that sometimes is more time. Right, so that's the one, I guess, as before class, I realized that one might be more time consuming as far as the decomposition part. Right, this is today's attendance question. Let's look at a question where we have to integrate a function of a infinite interval. So integrating 8 over x cubed on the interval -infinity to -5. I wonder if you started doing your calculation before class, if you already have an answer. Recording it. Okay, thank you. Thank you. No, that's not the one. Thank you. Question for this, well, you would apply power rule, but at infinity, the function integrated into a 0. Infinity, the limit value of the derivative is 0. That's really how you handle the lower limit. Upper limit is like the universal value. Well, let me send you the link, but you can definitely bookmark the link next time you wait for me to send you the link. It can stay in your device. Are you able to open the link? Let me- Aaron, are you opening the link? Okay. Remove this and then, can see if we are getting the same answer out of this question. What we can do, we will, the lower limit of the integration is steady. So we're gonna integrate from a finite. Let's say we integrate a to the negative 5. Of the function 8 over x cubed dx. So this is actually, a times x to the power of negative 3 dx. So with power, we have 8 times x to the power negative 2. The power plus 1, negative 3 plus 1 is negative 2. So that's what we have. And this is equal to 8 over 2 is 4, so negative 4 is the coefficient, x to the negative 2. I write it back to the back fraction, it's negative 4 over x squared, because negative power division. Now we have to evaluate at negative 5. And then a. So this is equal to negative 4 over negative 5 squared, which is 25. Right, and then minus negative 4 over 8 squared. That's how it is. And then we make a goes to infinity. If a goes to infinity and negative infinity, then a squared goes to infinity. So it's 4 over infinity. At 4 over infinity, the limit value is 0. So basically, the lower this number, it goes to 0. The limit value of that part is 0. So negative 4 over 25 is the actual integration value. It's the integral value. For the lower limit of a, when a goes to negative infinity, 0. That's the process. This is similar to the most question that we had on the 6.6.
Is the test still on Thursday or did you push it back?
I push it back to next Thursday.
Thank you so much.
It's next Thursday. You guys mentioned the time. So I was gonna change it last Thursday, but the George review just won't switch the file. It's already have a file there, but I deleted the old one now.
So it's just.
Yeah, the schedule has changed. There's a new schedule. Okay. Aaron, I still don't see your answer. You have. Oh. Any homework question before we start? Any homework question?
6.3.
Okay. You have a similar one like this? So it's 4 minus x squared, so we should do a sign substitution. So we would make x equal to sine theta. Right, so what we're gonna do is we make so x equal to 4 times sine theta. So I have a 4 in the x because I'm trying to match the 4 before the x. So 4 in here, 4 in here, so then they have coefficient. 2 times sine theta looks better, right? 2 squared is 4. Yes, it's my fault. It should be 2 times sine theta because x has to be squared. So that way we will have dx, which is equal to 2 times cosine theta theta. And that's what we're going to replace the dx in the numerator. In the other hand, we have root of 4 minus x squared, which then equal to 4 minus x, x is 2 sine theta, so x squared would be 4 sine squared theta. Now let's make it short. If you take the 2 out of the root, the 4, take it out of the root, become 2. And then after the 4 taken out is 1 minus sine squared theta, which is cosine theta. So then the root part is really 2 times cosine theta. So then this is the equal to, then make sure every part is replaced appropriately. dx is 2 cosine theta. And then the denominator is, there's an x, and x is 2 times sine theta. So x is equal to 2 times sine theta. And the root is 2 times cosine theta. Right. That finished the substitution part. That's switching from a question with x being the integration variable to a question with theta being the integration. So that finished the trig substitution. Now we calculate the integration with the trig value. Trig integration is what we learned in 6.2. So here, if you feel like it's a little bit difficult too, that might need some practice over what we were doing in section 6.2. We cancel some common factors. The 2 cosine theta is canceled, and then you have 1 over 2 sine theta. We need to we can bring the 2 outside with 1 over 2 integration. When you have 1 sine theta, that's really cosecant of theta, e theta. Here you're going to know a little bit how to integrate cosecant theta. As we mentioned before, we didn't train the formula for integration of cosecant theta, but we have the integration for secant theta. You remember what's the integration of secant theta? Anybody? How do you integrate secant theta? If you integrate Kylie, yeah. What's the integration of secant theta? Of secant theta? The integration of secant theta. I'm not sure. But I would do. Did we mention that in trig when we are doing the integration of trig function, trig integration? We talk about integration of secant, integration of secant cube. And we mentioned that these are the kind of function that can be time consuming. Is better to remember the formula. So integrate secant. Oh, secant. How about the natural log of secant? Yes. So what about the integration of cosecant? It should be similar, right? Think about something negative. Negative natural log of cosecant. Cosecant plus cotangent, yes. So integration of this function is very similar to integration of secant theta. Remember integration of secant theta. Secant is 1 over cosine. Cosecant is 1 over sine. Secant theta d theta is integrated into natural log of secant of theta plus tangent of theta. So co-functions have very similar results as far as integration and differentiation. So cosecant has very similar result to the secant, except we have a co-function, so it's negative. So it's negative 1/2, and then we have natural log of cosecant of theta plus cotangent of theta. Plus theta. So you can consider this as a corresponding volume of cosecant, since the volume secant is that. If you remember how do we, if you forget how to integrate secant, what we did is multiply numerator. Secant is really 1 over sine, or you can consider secant over 1. So multiply numerator and denominator by secant plus tangents, and then denominator is the derivative of numerator, which is why we use natural logs to manage that equation. So the whole idea of it is to create a natural log, a denominator has a function, numerator has a derivative of the function. Whenever that happens, natural log will be the answer of the antiderivative. This similar, it's very much the similar process. You multiply numerator denominator by the cosecant plus cotangent, and then the derivative of the denominator is numerator, except negative there. So anyway, now we finish the integration part. Once you finish the integration part, we were supposed to write into all these two has to be replaced by the x variable, because after all, the question is to integrate x as our integration variable. So we're gonna look at what does it look like, and consider how to go from, we have the sine value, sine of the angle is x over 2. So if you have sine value, draw a perfect triangle. You can go from sine value to cosine to tangent to cotangent. So all these values can be devised if you have understanding of the triangular trig function. So we're gonna go back here, go back to the original identification of your substitution, and that's how x equal to, but from x equal to, you can see the sine theta is equal to x over 2. So this is a division. And so you grab a triangle. If this is your theta, sine theta is opposite over hypotenuse. So x is opposite, 2 is a hypotenuse. So in the triangle, we have a right triangle, the opposite side of the angle, let's say x. This is a 2. So x over 2 becomes sine theta. We literally are trying to represent the sine value into a triangle. Now, on the other side, which is the adjacent side, for that triangle, we try to label all 3 sides. If that's 2, that's x. The third side is 4 over root of 4 minus x squared. That's third side. Often, what's in your integration question will show up also in your triangle. We're trying to use that triangle to represent all 6 trig values. Having one trig value causes all the other trig value being represented in the triangle. I have x and 2, that side. Adjacent side is going to be root of 4 minus x squared. So you would write down root of 4 minus x squared. Because suppose the adjacent side is a, then a squared plus x squared equal to 2 squared. Therefore, 2 squared minus x squared would be the a squared, and root of that would be the a. So a is the adjacent side. So now we have that side, and we can start writing down all the values. For example, cotangent value. We need the cotangent value in the final answer here. The cotangent is equal to cosine over adjacent side over opposite. Like tangent is opposite over adjacent, so cotangent adjacent over opposite. So it's going to be root of 4 minus x squared, root of 4 minus x squared over the opposite, which is x. That division goes for the cotangent, and the cosecant is going to be reciprocal of sine. Since we have sine equal to x over 2, then cosecant is 2 over x. So then the answer, going back to the original variable, is negative 1/2 natural log of 2 over x plus root of minus x squared over x x value. And then see. So this will be the answer for the final question. Hope that explains. We can rewrite it. You can have 1/2 natural log of this minus natural log of x. You're gonna switch out to like a little bit easier to input, but overall this should be okay. And we can double check if that works. Negative 1/2 natural log. And inside we have 2 over x for the secant, and then square root of 4 minus x squared over x with the tangent plus c. See if it, that's how it's being entered as. Any other homework question? That's 6.3 for the substitution. Try to finish the majority. For today, we started at 6.6. That's Thursday, so we're trying to finish. Right, on 6.6, we deal with some of the special integration where either the integration limit involves infinity or the integration function involves infinity. So we started with when the integration limit integration bounds infinity. We're talking about if any of the integration interval, if the integration interval involves a endpoint that was infinity, what we can do is we change that to a finite integration limit. And then after we got a formula for the integration value, we can then have that function's value, have that limit value calculated. So we would switch to A to B integration and either let B go to infinity if the upper limit goes to infinity, or let A go to infinity if that's infinity. Now, if you have to integrate some function from infinity to infinity, what you can do is find a middle point and integrate from A to infinity and plus negative infinity to H. We can separate a big integration to two small integrations by separating the integration interval. That was the plan. And because in the study of improper integral, which involves limit calculation, limit can be exist or does not exist. When the limit exists, we see the situation as a convergent situation. If the limit does not exist, and we see that's a divergent situation. So we see the integral diverges. And we did this few examples before, right? The other half that we didn't talk about is what if the function goes infinity? So sometimes the limit goes infinity. What if the function goes infinity? This is a situation that you have to identify the point where the function goes to infinity. It sounds difficult, but when you actually look at a particular example, it's not that hard to understand. For example, when we have infinity, for one particular example is when the denominator division by 0 is a situation. So these are two examples. So for example, if you have to integrate from 0 to 1, 1 over x, it sounds like the integration limit is finite. 0 to 1, 0 and 1 are both finite. But then the 1 over root of x, if x is equal to infinity, then that 1 over 0 is undefined. And the limit of 1 over root of x when x goes to 0 is infinity. That's why the value actually is really large. But in the division, with the denominator approaching 0, the whole thing goes to infinity. So that's when the function goes to infinity. So limit, integration limit go to infinity, improper integral. When the function goes to infinity, that's also improper. The two separate situations. Now this one also 1 over x squared. If x is near 0, x is really close to 0, then 1 over x is really large. It's end up being a really large value. And let's try to see how we calculate it. The way we handle it is identify the problem points and not to touch it at the beginning. And once we have a firm handle of it, and then we calculate that limit out. Right, so what we're gonna do is see this one, the problem point is 0. The 0 would be an issue. So anything that gives you an issue, you make sure you don't do it immediately and you go close to it and then try to inch in from there. Like try to approach something scary instead of just go direct at it, you change it to an A. So A to 1 over x dx. That's what we're gonna do. Right. this calculation, once we have a formula for this calculation, and then we make a go to 0 and find that limit value. So to calculate this, realize this is integrating from one number to the number, we have x to the -1/2, or if you finish this integration, we have to apply power rule. Power rule, according to power rule, whenever you're integrating, the power increase by 1. So -1/2 plus 1 is positive 1/2. So the integration is x to the power 1/2 over 1/2. And there's supposed to be plus c, but I'm just skipping that part. So this actually is behind x to the power 1/2. Or you can say this is actually 2 times root of x. That's the integer function. And we were supposed to make the value go to 1 on the upper limit to a on the lower limit. To calculate this, we would have 2 times root of 1 minus 2 times root of a. That's calculating it. Root of 1, of course, equal to 2. So this whole thing actually is equal to 2 minus 2 times root of a. Okay, so let's calculate this. This is going to equal limit of. Now that we have this calculated, we can now make a go to 0. In the formula, 2 minus 2a. And turn out the value 2. Meaning if a goes to 0, the value should be 0. Okay. So answer for that one will be 2. So it's finite. You know, there's a problem. Any question? Different from my understanding. So I use the degree. Right, yeah, the calculation was okay, right? I did the calculation at a line. Yeah. Let's see. Let's try to confirm this. When I'm doubting myself, I like to try to look at more. The calculation looks okay, but intuitively, I'm thinking the picture in my head. So let's see, we're integrating from 0 to 1. And we're integrating a fraction. So the numerator was 1, the denominator is square root of x. It's 2. And those are the calculation steps. It looks much more simplified than what I did, but this is how our textbook is approaching this thing. This is a function of 1 over root 2. Okay? And then we're integrating from 0 to 1 below that graph. So just say, it's 1, right? This spacing is 1, area of 1. So everything else altogether, even though it's infinitely long, but the total area is actually a finite value of 2. It's interesting. So this is our first example. Any question? Right, so the plan would be just to try to approach the finite situation. And then for the infinity value, what we're going to do is basically find the limit value of the finite situation. So what we're going to do is, like the second one, we know there's a problem at 0. So this situation is not like that one. This one is problem at 0. 0 is a boundary value of the interval, but 0 is not at any of the boundary. So number one thing is we have to write it into 2 separate integrations. So we know that 0 x equal to 0 would cause a problem. Right, it's a discontinuity for the y equal 1 over x squared. So 0, let's say, is this function's discontinuity. Discontinuous at that function. This function is discontinuous at x equals 0. So what we're gonna do is we're gonna integrate it from -1 to 0, 1 over x squared, dx, plus we're gonna integrate from 0 to 1. So if any value is a point, the number one thing you have to do is bring that point onto the boundary, onto the integration limit, and then we approach that. Because really, if we follow the fundamental theorem calculus, only at the boundary would it be affecting the final calculation. Find the antiderivative, we'll take the boundary value, put it to the integer function with the evaluation. We're putting it in the boundary so that we can see how it's gonna affect the final value. The integration part should be the same. So then we can go ahead and calculate, for example, the first one. When we calculate -1 to b of the value 1 over x squared. X. So this is going to equal to, put into power rule, this is x to the power -2. If you integrate it, it's going to be power of -1. So it's x to the power -1 over -1. And write it a little bit better, it's -1 over x, actually. So side negative power, we're going to write it into a reciprocal, just so we understand how x value is affecting the overall value. And we're putting the integration limit b is the upper limit, b we're gonna make it b approach 0. -1 is the lower limit. So the upper limit is -1 over b. Minus lower limit is -1 over -1. It's negative, it's the lower limit. Negative cancel. This is -1 over b. Plus -1. Actually, there's 3 negatives here. So still negative. And then this first calculation is the limit and b approach 0 of -1 over b minus 1. Now, if b approaching 0 and 1 over b would approach infinity. So this one would have a negative infinity right there. Okay. That one is the negative infinity. It can't be negative infinity, it should be positive. Thinking like that. Right. Right, any mistake in the calculation, I'm trying to look at it, the integration was okay? Looking at b, it's -1 over b. Negative minus negative.
Did you just solve it with both sides? Yeah, just solving it with both sides.
Yeah, I was trying to calculate the first one. This is 1 over x squared, it's a positive value. This integrates the positive function from 0 to 1. So this integration, it may be infinity, but it should be positive infinity. I was looking at that one. And if x approaching 0, oh, it's approaching 0 from the negative side. You're right. So it should be like this. So it's approaching 0 from the negative side. So basically we are having, this is a 0. This is -1. This is +1. What we're calculating right now is from -1 to 0. Okay, so we're calculating -1 to b is here, b is over here. So we're making b approach 0 from the negative side. Is that going to make sense? So b is really approaching 0 from the negative side. So b itself is a negative number. So b is a really small number, almost 0, but it's negative. So 1 over a negative number, that's negative. But negative of a negative b is positive. So that is a positive infinity. So it's positive infinity minus 1. You might have was going over this negative positive thing. So this entire thing actually equals the infinity. For the same reason, that one also equals infinity. So the entire integration actually is infinity. I mean, infinity plus infinity is still infinity. So this is diverging. It does not approach any finite number. The whole area goes really, really large. I was going like in my head, I was thinking, why do I get a 1/0 is infinity, but it's 1/0, it's negative infinity. And then negative infinity. If you look at the picture, this is why I was hesitating and have this image in my head that the behavior of y squared is completely positive. So you only look at the behavior of the function between negative and positive 1. So that's how it looks like. And we draw a x equals -1 to x equals +1. So then the area below the curve is positive, and you can see that this is why it's divergent. In between the graph, the area in those two bands is really, really tall, right? Infinity. You can't really bound it that well because this is too steep. So open up into a wider range than the 1/x or 1/x would be better. Any question? The mathematical calculation, I think, is not difficult since we are familiar with the power rule. But understanding it in the limit term, sometimes it's not that straightforward. So we have to actually look at the limit value one by one. Especially, like for me, I overlook the fact that we have a boundary value b, which is essentially a one-sided limit. So we're approaching 0 on the left side for the first example. On the right side, for this one, we're actually going to calculate a limit of, we're going to make b goes to +0, approach 0 from the positive side because it's going from that direction. It's two separate calculations here. And here it's going to be like 1 minus 1/b. Be approaching 0. Still negative 1/, yeah, 1 negative. This is also negative. I think it's a similar. The two is symmetrical. It should be a similar value. Still be going to be negative -1/b. Similar situation. So one side limit, sure. The right side limit, and that one is left side limit on the negative side. For improper integral, we one of the easier way is to identify the actual behavior of the function, and then maybe we'll have some understanding why sometimes it's infinity, sometimes it's not. All right, let's try to summarize what happened. We have these two similar examples. Here we have 1/x to the 1/2 power in the denominator. Here we have 1/x squared in the denominator. So I changed the power from 1/2 to a 2 since it changes zero. So for that finite interval, if you integrate a small power for the x in the denominator, it seems to be finite. But then when you have a bigger power, it ends up being an infinity on the element calculation. So what would be the pattern here? So turns out if the 1/xp have a power function in the denominator, that power, when that power is too big, it will converge if it's finite to infinity. So if you have that 1 to infinity, then that power, the bigger the better. But if you're integrating from 0 to 1/x to the power t, then the bigger power actually causes divergence, smaller power actually. So it concerns about where the limit that one is. So 1 to infinity and 0 to 1 are two separate situations. Okay, so this is for when the limit involves infinity and we want the denominator to be bigger power. The reason for that is if the limit involves infinity, then higher power means that the denominator goes to infinity, right? If the denominator goes to infinity, then 1/infinity goes to 0. I mean the limit value of that x derivative value will be converging. That's this. And now if you have a finite limit, let's say if you integrate 0 to b, then 1/xp when x equals to 0, the 0 will be a problem. this kind of improper integral, then only when t is smaller, it will converge. But it will diverge when t is larger. Separate situation, so it goes opposite. Because when you see when this number is smaller, higher power causes the denominator to be small. And then 1 over small number causes to be infinity. So we want the power to be smaller, just so the denominator will not get too big, and the whole fraction will not get too big. So in here, the denominator is big is good, because the denominator actually goes to infinity. But in here, the denominator, we don't want it to be too big. Because the denominator is small number, right? The denominator is like this number small, near 0. X is near 0, so we want x to have small numbers, smaller power. So in this case, the p has to be less than 1 for it to be converging. But in this case, we want the p to be bigger than 1 for it to be converging. It's related to the limit calculation for a different limit. If x goes to infinity, then we want the power to be bigger. So then the big values in the denominator is whole division to zeros. If x is approaching 0, like 0 is involved in here. And 1 over 0 is on the sign, and the denominator is really small. For smaller x value, the key better be small. Smaller value, so smaller power that makes sure the whole thing is fine. I keep seeing the same thing. I hope that kind of makes sense. Try to compare them to see some pattern. Another way is to actually graph the function to see how the area below the graph looks like. More experience, better, so we have better understanding. This is two types of the improper integral with negative power and how we handle negative power. Test. So sometimes we try to compare two different functions to see if the divergent converge situation. We will talk about this more when we are studying theories, but now we look at two functions if they're comparable, especially when they're both positive, I guess. All right, so you have two functions, they're both positive, and I think they're both bigger than 0. F of x is smaller than g of x. So that's the situation what will happen to the integration. The thing is, integration will keep the comparison. The comparison one smaller than the other one, and in the integration the same way. So you would say the integration, they're both positive. Right? They're both positive. That means positive, right? So integration of f of x on 0 to infinity will be smaller or equal to integration of g of x. Okay, so then because the function itself has that inequality relation, then the integral have the same direction, same kind of comparison between the two integrals. So you get the idea. Suppose this one is finite. Suppose this integration equals to a finite number. This one is converging. And as a consequence, if this one's finite already, it's small enough, then this one is smaller than the finite number. That one is also converging. So the first conclusion says if the g of x integration is converging, and then f of x also converging. So converge is converge on the bigger function. The bigger function converge, smaller function definitely converge. Now diverge is another situation. If f of x is smaller than g of x, but somehow f of x diverge. Suppose f of x diverge. What do we mean by f of x diverge? They're both positive. The functions integral into end up diverging. It means that this integration is infinity. So this integration has the infinity value. Therefore, this integration being bigger than that integration, that's infinity. So this is bigger than infinity. What can it be? If you're bigger than infinity, it has to be infinity yourself. So that the second conclusion says if the smaller function diverge, then the bigger function has to diverge because it pushes things to the bigger side, right? The smaller one is already in the infinity, and the bigger one is forced to be infinity as well. So that's the second conclusion. Right? So if we have that understanding function compare in that way, integration compare that way. So if this diverge, this converge, then that converge. If this diverge, this diverge. They don't diverge or converge simultaneously. They don't always do that simultaneously, but sometimes one will give you a conclusion on the other one. But we have to remember that order. For example, if this one converge, it does not guarantee this one converge. Smaller one equal by the number, bigger one may not. Okay. Another thing is if this diverge, it doesn't guarantee that one. I mean, if this infinity, it doesn't guarantee that one. So you have to remember that they have that squeeze effect. Bigger one being small causes small one being smaller. Smaller one being big causes bigger. That kind of makes sense. That's comparison test for integral. It allows us to make conclusion on a situation where integration itself is not possible. And you can relax the function, change it to if like this integration is difficult to calculate, let me make it smaller and calculate an easier integration. If that one, let's say converge, and then now this one is converged. Using conversion, we can make calculate or make decisions easier. If you don't have to calculate it, you just want to make a decision on the diverge or converge, then conversion test is helpful. Okay, for example, we're here on the board is two scenarios, like the first one. The first one is one of those situations we do not have antiderivative, so we will not be able to come up with a formula for integration e to the negative x squared. How do you integrate that? There's no formula. So what do? Let's relax that. E to the negative x squared is really small, but for any x value bigger than 1, e to the negative x squared is smaller than 1 over x squared. So we end up calculating 1 over x squared. Integration 1 to infinity 1 over x squared. We calculated before, it converted. So therefore, this converge. So this one, even though we don't have a formula for it, but we know it's equal to a finite number. Whole integration should have a value, even though we don't know that value. So that number, you can do a numerical calculation. You can use computers to come up with the appropriate number for it. Second scenario is that one, and that's really difficult integration as well. Because see, x squared minus 1 will be easier, but x squared minus x, you have to complete the square and then do a substitution. So calculation is difficult. Instead of doing that, we relax it to 1 over root of x and do 1 over root of x. By integration from this to this 1 over root of x, I think it was diverge. That was diverge, right? Yeah, I think so. So I think that one would also diverge since they have similar behavior. And that will be a good day. Okay, tomorrow let's look through the homework question. They were also assigned. Entire chapter 6 homework was assigned. Let me know if you've got any questions. We should answer the question. If you haven't answered your question yet, this is the question that we had earlier. The answer is A.
Oh, it didn't. Oh. What about